we are engineers from Twitch. My name is Yueshi, this is Jeff. We're going to talk about how we build our in-house software named TwitchTranscoder to deal with live streaming. So first, to say a few words about ourselves. Jeff, you are the new blood. You please.
Hi everyone, my name is Jeff. I want to thank Yueshi for giving me the opportunity to help him finish his presentation. I'm a new engineer on Twitch's transcoding team. I just graduated from UC Berkeley, so if there are any Cal alumni, go Bears. Yeah. I also worked as an intern on Twitch last summer where I helped them build out their ABR algorithm. So this has been an exciting introduction to this world for me. So yeah, thank you for the opportunity.
And welcome to the team. My name is Yueshi. I'm a principal research engineer at Twitch. I'm managing the transcoder team. So a lot of people, like including my dad, ask me, what do I do? I just describe in one way, I make pixel look prettier. So I'm responsible for all the low-level video technologies at Twitch, including codec, HLS, playback compatibility, latency, video quality, etc. So today, first of all, I assume most of you know what Twitch.tv is. If you don't feel sorry about that. Check it out. So what we are, in case you don't know, we are a social video platform. What does it mean? Viewer comes to our site to watch broadcast or gamer playing game and interact with the broadcasters. So in this example, so this guy is broadcasting, playing a game, and his viewer is chatting with him or chatting with each other, basically interacting with him. So majority of our content is live, although we also provide VOD. So we are a user-uploaded live streaming platform. Talking about our size, this is last year's number. We have reasonably big viewership, but what I want to point out is we are consider us as an international TV station on internet. And I myself, coming from linear TV background, at our peak, we ingest more than 40,000 concurrent channels. I would imagine there is no TV station in the world offers 40,000 concurrent channels. And at the moment, Demuxed is one of them. So based on that, you can imagine that our budget for transcoder, it's really different from traditional TV stations. We really cannot afford like a professional $20,000 transcoder for every channel. That will make us out of business. So density and also robustness are critical to our business. So based on this business need, I will explain later that why we just cannot use FFmpeg. We have to build our own in-house software called TwitchTranscoder. So let me say a few words about the general architecture. You don't have to understand. This diagram is not supposed to be understood. But I just want to show you that. So the inputs, we're taking 1080p60 input. We are not, I mean, although we do have live streaming product, but most of the content is high quality 1080p 66 megabits per second or higher. So it's a broadcast quality. And I have a crying face here is we try to offer as many transcoders offer transcode to as many channels as possible. However, there is still a proportion of channels based on the viewership that we cannot offer transcoding, so we offer transmuxing. So this means we are converting, just repackaging from RTMP 1080p60 to HLS 1080p60. However, the most interesting part of our transcoder is we transcode and offer this full ABR ladder. And I want to emphasize that the top 1080p60 is purely transmuxed, not transcoded. This is for two reasons. First, as you know, I think all of you are MPEG experts. Are you? You know, MPEG is a lossy standard. Every transcoding will trigger some generation loss. So we will actually lose quality. The second one, which is more important, as I mentioned earlier, that computation cost is extremely, it's very precious resource for us. So we do not want to spend our CPUs on transcoding the source, because we already have it. So we just transmux the source. So we are doing a hybrid, transmuxing the top source 1080p and transcoding the rest. So this is the overall, the contract of our live stream transcoder. Okay, next I'm going to talk about FFmpeg. It's a lovely piece of software. I guess all of you agree. We love it. I have to give a joke that I myself coming from a linear TV background, and I also work for a semiconductor company. Many years ago, when I just started my career, transcoding or encoding really have to be performed on ASIC. And there's no other way to do transcoding. If you open up a video textbook, they always say that. However, when later on, like a lot of hours of video are actually transcoded by FFmpeg. So I was joking to my colleague at that time. I said, every time we don't get a pay rise or we actually lose the business, it's because of FFmpeg. It's a great piece of software. And in fact, it's actually so versatile. It's so capable. It's doing so many things, including it can do live streaming transcoding. So here I give you an example, like in order to do one in and one out, so one rendition in and one rendition out, this is the command option you can actually use. So let me say a few words about that to explain a little bit more. So you have the input RTMP endpoint, like RTMP / etc. And these are the encoder, like video encoder, video audio encoder parameters, but ultimately what you want output this, output an M3U8. And this is X264 option that I want to deliberately turn off the scene change detection so that every X second I'm going to start an IDR. I'm starting an IDR so that I start a new segment. So this is what this is about. So for example, if we're dealing with 60 frames per second and I want to slice the segment always at 2 seconds, I put this IDR interval as 120. All right, and the rest, I guess it's pretty, you guys pretty familiar. It's the resolution, what resolution you want, what the frame rate, what's the target bit rate, what's H.264 profile, like main or baseline, and you want to transcode it to AAC, and which scalar algorithm you use. This one I want to explain a little bit that because we do live, our playlist does not contain all the segments, otherwise it will be thousands. We only contain the most recent, for example, 6 or 7. So this is the option that you want to put in how many segments you want the playlist to contain. And if you don't want to do transcoding, you can do transmuxing. It's a lot simpler. You just copy the video and copy the audio. So in this way, so this is one in and one out. So for our full ladder, you actually need to spawn here 6 instances of FFmpeg. All right, so this is one in and one out. On the other hand, FFmpeg does provide a mode that you can do one in and n out. This has a few advantages, which I will explain later. But as you can see, how it works is you still specify the RTMP, but you can specify a number of outputs. So each of them is associated with one HLS rendition. And in the same way that if you want the first one to be transmuxed, you actually do in this way. All right? So far what I would say, FFmpeg does provide this functionality. It is working. If you don't care about a few things, which I will explain later, this is a solution. If you only have 5 minutes to fire it up and make it working. So thanks, FFmpeg. So it's a great piece of software. All right. So next, I'm going to talk about why we choose to put in all this effort to build our own TwitchTranscoder. Why I'm still having a job. One thing is, in HTTP, a continuous video stream has been sliced into segments. So each segment, there was one HTTP request associated with it. So in this example, that we have 4 variants, and the top one, for example, is 1080p, and the next one is 720p 60, etc. So it is very important, and if you want to make your output HLS or dash spec compliant, you have to align the segment perfectly, which means the first frame, which is IDR for H.264, its PTS, its presentation timestamp, must be same, exactly same, across all the variants. So in our engineering practice, we found that if you only do it just off by 1 frame or half a frame, it actually will make some third-party player cry. So I spent a lot of time fixing one issue on Chromecast. It's really because we had a bug in our transcoder. We just got this wrong by a little bit. So takeaway message is in order to make your stream spec compliant, the segment have to be perfectly time aligned for seamless switching. However, as I explained, what we want to do is we want the first rendition or first variant be transmuxed, not transcoded. Because we transmux that, we do not have control on the IDR interval. The IDR interval is completely controlled by the streaming software. For example, it's the OBS or whatever software. So OBS software encoder, it might choose, oh, here I have a scene change detection. So I detect a scene change. And I will have to insert an IDR. But on the other hand, the other rendition does not know about it. The other renditions are running independently. So in this case, you will actually have this problem. And ideally, this is what we want. We want the transcoder rendition to follow the IDR interval of the source. So this is what we want. The second is the software performance. As I mentioned, that the operation cost is very critical for our business. So if I run it not 1 in and 1 out, if I run it 1 in and N out, so I only need to have 1 decoder. And 1 decoder actually associated with a few scalar and then 1 encoder. So each pass is actually associated with 1 transcoder rendition. So ideally, we want all these, because scalar and encoder are all very expensive. So ideally, we want all of these boxes running concurrently, utilizing CPU to maximum. All right? And on the other hand, if you think about scalar is also very important, it's also very expensive. So for the 720p and 720p60 and 720p30, they are actually doing exactly the same scaling job. So why not just combine them and do not do redundant scaling? So this is like a simple threading model that we put into our software. Is just in order to make 720p60 and 720p30 to share the same scalar. So here the scalar agent, instead of they just do the scaling by themselves, they first ask, do I have this frame already scaled in the shared buffer? If not, go ahead and do the scaling. So these 2 threads are sharing the same physical scalar. All right, so I have talked about 2 issues. I've talked about the IDR alignment. I've talked about the software performance. There's one last thing is there are a lot of custom features, as you all can expect, that Twitch provide a lot of features so that bring our user very specific or proprietary experience. And one very interesting thing that what I found is, as I mentioned, we are an international TV stations. We receive 60 frames per second. We also sometimes receive 50 frames per second. I live in Australia for many years. Like Australia, Europe, they are power countries. So if we do receive the source as 50 frames per second, we really don't want to downsample that to 30 frames per second. We want to downsample that to 25 frames per second. So how do we do it intelligently? Sometimes the video does look like a 50 frames per second because it is actually original 60 frames per second, but with some dropping frames, so it looks like 50 frames per second. So how do we design this downsampling intelligently to deal with all the cases? So that's also the smart that we put into our software. I guess I got to shut up here. I let you, Jeff, to present the result.
All right, so I'm going to take over for the rest of the presentation and talk a little bit about the architecture and threading model of FFmpeg, which is, of course, very important to us. So we did make some claims. Obviously, this entire presentation was about how FFmpeg is an awesome tool, but it perhaps isn't the most optimal for the live stream transcoding, which is when we have that one input stream and we have that mix of transmuxed and transcoded N outputs. So I don't need to convince any of you guys that the video transcoding pipeline is pretty expensive. So obviously, we're going to want to do things as efficiently as possible. We're going to want to utilize our CPU resources to its maximum. And this is so we can optimize for the viewer and amongst things like reduced latency. So that's why we took a look here into the threading model of FFmpeg, because we do want to do things as efficiently as possible. And what we found is that FFmpeg actually initializes a number of worker threads based on the number of inputs you pass in. So in terms of how many threads are actually orchestrating the work done by the transcoding job, we actually have a single thread for this one input live streaming example. Now this is kind of important because this means we're doing our work sequentially. So I've got a probably pretty hard to read snippet of code up there. This was taken directly from the FFmpeg open source repository. And this function, I chose this one for two reasons. One, to kind of demonstrate what I mean by this sequential sort of processing. So if you just like follow along with this pseudocode, some of the innards have been redacted to just break it down to its core. But essentially we have this for loop at the very top. We're going through every output stream that we've specified when we ran the command line tool. And then we're just going to go ahead and take that output stream, grab a frame that's been filtered up until this point in the pipeline, and basically until it's done, we're going to process one output stream at a time. We're going to call either do video out or do audio out, depending on the type of the video frame, and that's going to send it to our encoder. So as you can see, this is kind of like doing one thing at a time, which is not necessarily something we want. The second reason is because the encoder that we specify here is actually pretty important. We use libx264 in production, which I'm sure many of you guys are familiar with. And libx264 is a multi-threaded encoder. So we've reached this point where I'm talking about encoding, which is the most expensive part of the pipeline, and it actually is multi-threaded. So why are we spending so much time talking about everything beforehand? Well, indeed, if you were to run FFmpeg with this example that we're talking about, you should see that there is work scheduled on all of the cores of your machine. But what is also true is you might not be reaching full capacity, so there might be a lot of resources that are underutilized. And there's a variety of reasons that this could be. The one that sounds most feasible to us is because, like Yueshi mentioned, there are upstream filters that are very computationally expensive besides the encoder that have not been optimized in this particular scenario. So theoretically, libx264 should be able to fully utilize its resources if you throw in frames to it fast enough. But if the scaler, for example, is lagging behind, this might be a little bit problematic. Now, this is in contrast to what we've done with TwitchTranscoder. The difference in the architecture here is that for every filter upstream, so this could be like resampling, this could be scaling, these all run in its own independent thread, and it has a queue of frames that it's ready to process. So what this means is that every filter that's computationally expensive is doing work as fast as possible without worrying about being bottlenecked by its neighbors. When it's done, it's just going to pass that frame to the next point, and we're going to move on from there. So to quantify our results, the only way we can really do that is by running some benchmarks for our tool against theirs. So again, FFmpeg is pretty awesome. As we see here, we took in a 1080p 60 FPS video, and using the same configurations, we ran our tool, producing a variety of renditions against FFmpeg. So here, this is just 720p 60, and we actually see that FFmpeg performs marginally better than us, which is pretty cool. The reason for this, however, is this is the one-in, one-out use case, which we don't really get any optimizations from doing all that multi-threaded work. In addition to that, we're handling some proprietary metadata, we're talking to some other services, so this might slow us down a little bit. Where you start to see the benefits is when you add more renditions, obviously. So here, 720p 60 and 30, we're getting the savings from the scaling, like Yueshi talked about, whereas FFmpeg just has more work to do. And this last example is just the entire transcode stack that we offer to our viewers, everything from 720p 60 to 160. And so here you can see the margin has grown considerably larger. Now this entire time, we've been giving TwitchTranscoder cheaper and cheaper renditions to process, which is why it's not increasing too much in time. But these are just more loops for FFmpeg to go through, so this might be causing that marginal gap. So I've talked to you guys for a few minutes now about just how important it is to do things as quick and efficiently as possible. And this was all made under one assumption, which is that we're running that single instance of FFmpeg producing those N outputs. And as people on the mailing list and stuff like that will tell you, there's other ways to use FFmpeg. For example, you could run multiple instances, each doing just one job. So each taking in the same input, and each producing a different transcode that you want. And so we actually did, obviously, run around with this example as well. And what you will see is that your CPU resources are going to be a lot better utilized, but it's also a double-edged sword for 2 reasons. One is you introduce a lot of redundancy into your system. If you have 5 parallel instances of FFmpeg, you're also decoding 5 times. You're not getting the savings from the scaling. And number 2 is, depending on how you run these parallel instances, you might not guarantee IDR alignment as well. And so this means that we can't really offer ABR, which means all the work I did last summer was for nothing. So that kind of sucks. The very last thing I want to talk about, this is obviously impossible to read. This is just to really show you the ceiling that you can also hit when you're running multiple instances of either tool. No matter how beefy your computer is, you will run into a limit, and what Yueshi talked about is we want to achieve maximum density. So at some point on like commodity hardware, maybe 2 or 3 instances of FFmpeg, doing the transcoding jobs that we ask for it will run into some issues. So here I'm just going to choose one. All of that red text just says co-located picture order count cannot be found. And what this means is that we're trying to decode a frame, and it's looking for a p frame or a key frame to kind of decode from, but it can't be found. So what we assume is happening here is that we've reached a point where the FFmpeg instances are no longer able to keep up, and they're dropping frames, and these are very important frames to us. So the same amount of instances for TwitchTranscoder, however, can be run without running into these issues, even though we're both using the same underlying technology like libx264. And so what we conclude from that is we can achieve a higher density, we can scale a little bit better, and overall we'll save money from that. So I'm going to throw it back to Yueshi for a quick summary.
All right, thank you, Jeff. It's a great work. So let me summarize a little bit. So what we just discussed in the beginning, that Twitch is a social video platform. We offer live streaming, and we are an international live streaming TV stations, and we ingest a lot of video, which means our budget for our transcoder is very low, and the high density is extremely important for our business. I also talk about the contract of our transcoder. What this is supposed to do is supposed to convert live RTMP to HLS. This actually reminds me, like this morning, Netflix talking about their fantastic 250 kilobits. Wow, this is congratulations on the great work, but I just cannot afford spending 9 days to encode 1 hour of video. It needs to, every second must be finished in 1 second. So fortunately or unfortunately, this is the technical challenge that we Twitch engineers have to face. Also, I talk about FFmpeg, fantastic piece of software. It already offers live streaming, RTMP-to-HLS, transcoding, transmuxing. However, we found it has a few issues. The first one is the segment alignment, if we want to do both transmuxing and the transcoding. As well as we found it has software performance issue. So based on these requirements, we engineer build our in-house transcoder software called TwitchTranscoder to address these issues. But all the secrets come from a pretty sophisticated threading model. We basically make every component running at the same time. All right, I think that's it for our presentation. Thank you very much. Any questions?